Hi everybody, welcome to another video in linear algebra section 3.3. Actually in this section we learn a lot more than just Cramer's rule. We'll get back to inverse. And then the area of volume and transformation. So Cramer's rule is the first one, and then inverse, and then volume and linear transformation. So actually that's the whole title. I don't know why I skipped that for the title. Right, first part, Cramer's rule. Let A be an invertible n by n matrix for any B in Rn. The unique solution x of Ax equal to B has entries given by that. And of course we know determinant of A, and then determinant of AI B, meaning that we're going to substitute B, we're going to replace column AI with B, right? So that gives us xi. So now I can say xi is equal to, I just use d of I over d, and because the same formula, but this time we define AIB is the same as if we determine determinant of AIB, if we define determinant of AIB, we replace all of that by just DI, and we replace determinant of A by just D. Now if we use those two, then the Cramer's rule is a lot more compact form, right? So let's just jump right into an example. This is actually easier to do than to explain how to do it. Use Cramer's rule to solve the following system. So we have a few examples here. Right, so first we're going to have determinant of A. So I will write determinant of 8. And if we use the shorthand notation here, I'm just going to say D, which is determinant of the coefficient matrix on the left hand side, 1, 2, 4, 5. And so 1 times 5 minus 2 times 8. Minus 2 times 4, sorry. That is minus 3. Right, so that's the first one. Next, we calculate A determinant of AIB. So I'm just going to write that at first. Now, instead of use I, we'll go from 1 to 2. Since we have x and y, I'm just going to say dx and B. No, not big X, just regular X, sorry. Not boldface X, just regular X. So by this we mean I will replace the column B will replace into the coefficient of X. So in this case I will have D, just use X. And what we do is the determinant is that instead of the coefficient of x, we replace by 3 and 6, which is the last one. So we replace the last column into the x variable, and we just find determinant. So 3 times 5, 15, minus 2 times 6, that is 3. And next we will find determinant of, that should not write x, but since If this is x1, x2, then we write a1. That more sense. But since there's only x, I guess we can just write x or y. Here we'll replace the coefficient of y by the last column. So I'm going to say dy. So as you see, we have the matrix A, determinant of that's D. Now we just replace the last column into x. We have dx. Replace the last column into y. We have dy. But of course we have to calculate the determinant. Right. So if we replace that into coefficient of y, we still have 1 and 4. Our coefficient of y is still 3 and 6. So we have 1 times 6 minus 3 times 4. And that is -6. And after all of that, we will define x as equal to determinant of a x replaced by b over determinant of a, which we use it's just dx over d. Dx over d, so we 3 over -3 is -1, and then y equal to determinant of a y b divided by determinant of a. Then we have dy over d. Yeah. We like that in course algebra or in lower level, they just use dx and d. They don't write that complicated. And if it works, then why we just use that. Right. So we have x is equal to -1, y equal to 2. So that's simple. Of course, that is one way to solve the system equation. The best way to solve that is the linear use reduced row echelon form and apply to the augmented matrix. This still the best. By the best, I mean the most efficient way to do it. Not only that, we can find a solution where the solution, when there's no solution or infinitely many solutions, which is the limited, which is limit. I mean, it's not covered by the Cramer's rule. Right. 1, 2, 3, 4, 5, 6. Yeah, so x equal to -1, y equal to 2. This is the most efficient way to do that. I mean, the reduced row echelon form is the most efficient way to do that. Of course, we can also have the matrix equation. So x equal A inverse B. This method is not as efficient as the reduced row echelon form, and this one also is not efficient as the reduced row echelon form. So that will be the best. Of course, this was related too much work. Right, now let's look at another example on this one. So now I'm just going to use the shorthand notation here instead of writing using the determinant like that. Right, so actually just write determinant. Why not? Determinant of A 1, 2, -2, -4. So cross multiply -4 minus 2 times -2. 4 minus 4, so that's 0. Well, we know we cannot divide by 0, so that could be a problem. and then we find determinant of a x replaced by b, and so we replace 3 and 5 into x coefficients. And we have negative 22. Now we replace this into the y, coefficient of y. And then we have 11. Right. Because the numbers here are not really important. What important? They are not 0. And that is the problem. Now, of course, this we say this is dx, and dy. Now, back to the solution, we say x is equal to dx over d. Well, that of course by itself is undefined and therefore no solution. Right? If we use the reduced echelon form, you see that we have the pivot at the last column here. That is a sign of no solution. So that is correct. So it's no solution. We visit this in a minute. Let's just continue with this example. That equal to 0. Now dx right, so replace the last column into x. Right. Now replace 3 and 9, the last column, into the coefficient of y. Now, so does it better? Well, still divide by 0 is not good at all. So really cannot tell. Of course, if it is in calculus 1 indeterminate form, but it is not indeterminate form, because indeterminate form requires we have limits that approaching to 0 and approaching to 0. We have no limit here. So it's not indeterminate. So let's just do the reduced or echelon form. Right, 1, 2, 3, 6, 9. And when we do that, we see we have a pivot here. There's a free variable, so this one infinitely many solution. Won't be able to tell that in here. So that's why the grammar rule is not the best way to solve it, because not very convincing. It is okay when we show that's no solution, but for infinitely many solution, it's not very convincing. So right, so that's why I want to write in this little note here. First, of course, grammar rule, when there's a unique solution, it's easy. We have that. Now, what happens when we don't have unique solution? So when we have no solution, right? No solution is where we have d equal to 0, and one of the dx, dy, and so on are not equal to 0. Right. So what we have here, the d is equal to 0, determinant is equal to 0, but the dx is not, and we have no solution. And when we have infinitely many solutions, for infinitely many solutions, what we have is that all the d's have to be equal to 0. If that is the case, then we have infinitely many solutions. But even that, we do not have the we do not have the reduced echelon form matrix, so we can write the solution in terms of free variable. The grammar rule only give us that it is infinitely many solutions. It didn't tell in what form. It can tell you no solution too, but I said the best way is used to reduce the echelon form. Of course, the matrix inverse, this will be the worst, because if we use this, there's no way we can tell if there's no solution or infinitely many solutions. Right. So what we learned in the first chapter actually is the best. However, in some scenarios, some situations, the grammar rule will work very well. There's something like this where we have the s. We have some parameters in the problem where we don't have all constant, because the row reduced echelon form those steps, if we have the coefficient, if we have the variables in it, we have like s in that, it will be difficult to evaluate. Right. But still, it's more efficient than the grammar rule. Right, first, let's use determinant of 8. Or just use d. Will be 3s. That's the coefficient of x1, -2. And -6, and then s. Right, so that is determinant. One thing I also want to write, in case when there's a unique solution, in order to have unique solution, what we have is just d is not equal to 0. As you see, if d is not equal to 0, divided by something different than 0 is always defined. Alright, so we have no solution, the d is 0, one of the dx, dy, or so on is not equal to 0. infinitely many solutions, all the d's equal to 0, and unique solution is where the d not equal to 0. Right. Now, we find the determinant here for the system 3s, -2, -6, and s. Again, the same way so it will be 3s squared minus -2 times -6 is 12, so 3x squared minus 12. Right, just keep that at the moment. Next, we find determinant a. Now, if we have x1, x2, we can use the subscript. Or I just say it here. Of course, I can write 4 and 1 in this case, but that is rather confusing. I just write d1. It will be much better. So what I do is, of course, we place the 4 and 1 into the first coefficient of x1, and here we have 4s minus a -2, so 4s plus 2. Next, we find determinant of a2, b, that for the substitute we replace 4 and 1 into the coefficient of s2. So it will be 3s plus 24. Right. So that's what we have. Next. Now use Cramer's rule to determine which values of s the system has unique solution. So when we have unique solution, the determinant cannot be equal to 0. So unique solution is where d not equal to 0. So we have 3s squared minus 12 not equal to 0. So we factor out 3s minus 2, s plus 2. Not equal to 0. So we have x not equal to 2 and x not equal to -2. Factor out 3, we have s squared minus 4, which factor further into s minus 2 and s plus 2, and that cannot be equal to 0, so that's what we have, and for some reason I write x. And once we have that, when s not equal to 2 and x not equal to -2, we have the solution x1 is d1 over d right here. Of course, we can factor out 2, and we have s plus 2 on the top cancel with x plus 2 at the bottom, but it doesn't matter, just leave the answer in that form. Yeah, of course, like I said, factor out 2, and we have s plus 2 in the bottom, s plus 2 cancel out, but just leave it like that. So that's what we have. Once again, we could also write the solution as would reduce to x plus 2. We have 2 over 3 s minus 2. Right. Next, in this system of equation, all we need is to find z. So in that case, we don't have to find the x or the y. We just need to find the determinant, of course, and then the x. I mean, for z, just dz. Right. So d, of course, is determinant of the matrix, which I will write 1 for x, -1 for y, and 3 for z. 3x, 0y, 1z, 1x, 3y, and 1z. Now I'm just use a calculator just to save time. Of course, by this time you should know how to evaluate the determinant. Right, that is 26. Now since you only need to find z, we only need dz, which of course replace z, coefficient of z, by the last column. So replace the coefficient of z, but coefficient for x and y will stay the same. Just need to replace the last column here. That gives us the z determinant. So once again, if you cannot go up and hit enter to copy and paste, you can always hit second enter. So that's 52. So in that case, z is equal to dz over d. Yeah. Still, it's nice, and we don't need x or y. It's kind of nice, but doing that is still not efficient as the way we use to reduce for echelon form to solve the system of equation. By the way, when you get to differential equation, this will come in handy. Right, so that's the first part of this section, grammar rule. Now the second part is about determinants and inverse matrices. What we learned in the previous section is that if determinant is not equal to 0, if determinant is not equal to 0, the inverse exists. Or we say determinant not equal to 0, the matrix is invertible. And if the matrix is invertible, there's the other 12 properties that come with it. Right. Now, this is another way to find the inverse of the matrix. By the way, this is even less sufficient way than to reduce to echelon form. Earlier we said if we want to find the inverse, we're going to construct the augmented matrix in this form, and we do reduce to echelon form. The first part, A, if it is reduced to I, then what we have here is going to be the inverse. If we do not have the identity here, the inverse does not exist. I mean, it is there will be something there, but that's not the inverse. Yeah, so A has to be reduced to I for this to be the inverse. If this is not I, it's not inverse. This is still the best and most efficient way to find the inverse. Unless it is 2 by 2, there's a formula for the inverse. But I said in general, reduced to echelon form is the most efficient way of doing a lot of other things. Finding inverse, solve system of equation, to name a few. Right, now, how do we find the inverse if we don't want to use reduced to echelon form? Well, first of all, that's going to take a lot of time. And now remember, from the previous section where we say Cij is the cofactor of A, where we removed the row and the column containing I and j, and with the negative sign into it. I mean negative 1. So the sign will alternate positive and negative. That's what we define a cofactor is. Now, if we put the matrix of all of those cofactors and then we transpose it, it is called the adjoint or the aggregate of A. Denote adj A. So all the cofactors and then transpose, and you will see now why it is a lot of time. Right, now the theorem says that let A be the invertible matrix n by n, then A inverse is given by 1 over determinant of A times the aggregate of A or the echelon of A. Right, first let's prove the formula for A inverse of a 2 by 2. Well, first we just write all the cofactor C11. By the way, for the cofactor we have to consider the sign in the sign chart, starting from the positive, and it will alternate the sign in every direction. So C11, it's going to be positive, stand on the positive side, so just say positive. And we will cover the row and the column that contain in the element 8. When we do that, what's left? Just D, right? So that gives us D. Now, C12. 12 standing on the negative sign. And we'll cover the row and the column that containing B. In that case, it will be C, right? So negative C. Next, C21. C21 stand on the minus sign, the negative sign. And then we cover the row and the column that containing the C2, the element C. So that will be B. And finally C22, cofactor, that is the capital C22, standing on the plus. And cover the row and the column that containing the 2 and 3, and we left with B. Now, after that, we can form the aggregate of 8, or the echelon of A is equal to C11, C12, C21, C22, and then we have to transpose it. So this will be D, negative C, negative B, or that should be A. C22. If you cover the row and the column that containing the element 22, containing D, that will be 8. And then we transpose that. Transpose meaning rows become column. Row become column. And the second row become the second column. So that is the aggregate. And finally, according to that, A inverse equal to 1 over determinant of A times aggregate of A. For that matrix, determinant of A is equal to AD minus BC. So we have 1 over AD minus BC times the aggregate, which is this one. Right. Of course, we see earlier that for 2 by 2 matrix, that is the inverse. Of course, that is a lot of work. Talking about a lot of work for 3 by 3 here, this would be definitely a lot of work. So let A be that matrix. Now try to find the echelon of A, and then after that, find the inverse. Right. Before we do anything, let's just find the determinant of A, because if determinant of A equal to 0, it is not invertible. Of course, inverse does not exist, and we don't need to find it. Here's determinant. Right, 2, 1, 3, 1, negative 1, and 1, 1, 4, negative 2. Right, determinant is equal to 14. That means it has an inverse, because the determinant not equal to 0. So just put that in the back pocket. Determinant of A is equal to 14. Right. Now just in case, what is the inverse? Because we entered the matrix already, I don't want to type it again. Just delete this. And inverse. Change to fraction. Right, that's what we should have for the inverse. Right, now, in order to find the inverse using the cofactors, we have to find all the cofactors with the sign chart. That is the sign chart for 3 by 3. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Right. C11 for that. Cofactor is going to be a determinant, so it's on the plus, so that's plus. We cover the first row and the first column. Where's the other? Alright, so that's what's left. Right, so that gives us 2 minus 4. 2 minus 4 is minus 2. Right, that is C11. Now, C12. C12 stand on the negative sign. And just go over the row and the column that containing the 1, 2 entry. So we left with 1, 1, 1, and negative 2. So that gives us negative 2. Negative 1 is negative 3, with the negative again, that's 3. Now, C13. 1, 3 stand on the plus sign. That gives us 4 minus negative 1, so that will be 5, positive 5. Right. So that's C1, 1, C1, 2, and C3. 1 3. Right, next C21. Right, C21 stand on the negative sign. Yes, the calculation here sounds simple, but there's a lot of little computation. Right, so without the first column will be 1 3 4 negative 2. Right, so that is negative 2, negative 12, negative 2, negative 12 is negative 14 with the negative, so that is positive 14. Right, C22, C22, 22, stand on the plus sign. Now, 2, 2, so we have 2, 3, and 1, negative 2. Negative 2, negative 3, that's negative 5. But that is negative 4, sorry. Negative 4, negative 3 is negative 7. Now C3, 2, 3. C2, 3 stand on the negative sign. And according to the submatrix 2, 1, 2, 1, 1, 4. That will give us 8 minus 1 is 7 with the minus. Right. C31. C31 stand on the plus sign. Right. So be 2, 1, 1, negative 1. So negative 2, negative 1, so negative 3. And C 3, 2. 3, 2 stand on negative sign. And we have 2, 3, 1, 1. Determinant is 2 minus 3. 2 minus 3 is minus 1. Turn to 1. C3, 3. Standing on the plus sign. And it will be 2, 1. 1, negative 1. Negative 2, negative 1 is negative 3. Now, put all of this together to form the attribute of A. It's going to be all those cofactors, but have to be transposed. So I'm just going to write numbers. Negative 2, 3, 5, 14, negative 7, negative 7, negative 3, 1, and negative 3. Don't forget in the attribute there is a transpose. So rows become column. By the way, is that an option? No, they don't have that. Right, so that is the attribute of A. Now, to find the inverse, A inverse is equal 1 over determinant of A times the aggregate of A. Yeah. So we did find the determinant 14, so it's 1 over 14 times that. Right, multiply the 1 over 14 into all of this, negative 1 over 7, 1, negative 3 over 14. Right. 3 over 14, negative 1/2. Why is that one is not right? We'll go back and check that in a minute. Negative 7 over 14 is negative 1/2. And negative 3 over 14. Yeah, why that is not right? Well, let's see, where's that come from? Negative 2, 14. That is negative 2, negative 1. Oh, that's... Oh, wrong number. It's completely off here. Right. For 3, 1, that should be 1, 3, negative 1, and 1. Right. And so that gives us 1 minus negative 3, so that's going to be 4. So that should be 4. And transpose is going to be here, going to be 4. 4 over 14 is 2 over 7. Right. So that certainly works. Take a lot of work. And of course, we have to pay attention to, make sure everything has to be correct. So that's why I don't recommend you to do it this way. The best way to find the inverse, of course, if you have the calculator, but best way to find the inverse, if we have to do it by hand, is going to use this one, row reduced echelon form. It's still the best algorithm we have. Right. Now, on to the third part of the section, determinants and linear transformation. Right. Let T be a transformation from R2 to R2. It is a linear transformation and determined by 2 by 2 matrix A. If S is a parallelogram in R2, then the area of the new area in the transform is equal to determinant of A times the area of S. Let T be R3 to R3 be the linear transformation determined by a 3 by 3 matrix. If S is a parallelogram, at the three-dimensional version of the parallelogram, I can't even say that word, but anyway, the volume of that is equal to the determinant of A, the matrix of transformation, times the volume of S. I cannot say that, but I can draw it. So pretty much the parallelogram in 3 dimensions. It's not quite a box, so it might be so it is that the rectangular box is a special case of that. Right. So once again, we have here, which is S, and then we have the transformation T into something like that, and this is the transformation of it, transformation of S. And of course when the transformation T given by the matrix A, so in that case the area of that is equal to the determinant of A times the area of S. And that's what the theorem is about. Right. Actually this is very interesting. So let's look at this example. Now this the step to help us to prove not actually how to do this from step by step. For this step to find the area of the parallelogram determined by this point. So first I will plot this point -2, -2, 0 and 3, 4 and -1, and 6 and 4. So that is the parallelogram. Alright, so let's write the coordinates -2, -2, 0 and 3. These points are not given in a clockwise or counterclockwise, but regardless we have those points. Now so that's the first thing, draw the parallelogram. Now then transform it so one of the vertex is at the origin. So the easiest one is to move everything in this direction. So this point is going to be that. So the -2, 2 will becomes this one, and this will shift into that point 0 and 3. So we just translate everything +2 and this is the vector 2 and 2. So we just move everything in that direction. So that becomes 2 and 5. 2 and 5. 6 and 4 plus 2 and 2, so it will be 8 and 6. 8 and 6. And 4 and -2 plus 2 and 2 will be 6 and 1. Yeah. So all the coordinate +2 and +2. So I'm just going to say the transformation from here to here is we go from xy map into x +2, y +2. Right. So I have a parallelogram here. Now if we want to, we can write the coordinates 0, 0, 2 and 5, 8 and 6, 6 and 1. Right, so we have those. This is the parallelogram. Of course, the translation from here to here, the area is still the same, so we don't change the area at all. Next, find the transformation from T R2 to R2, so that is transform the unit square S to P, right? So I'm going to draw this parallelogram here. Right. Again, let's write the coordinates 0, 0, 2 and 5, 8 and 6, 6 and 1. Right. Now we'll ask to find the transformation to go from here to there. And what we're actually going from is the unit square before going any further, and then you ask, why do we have to use the unit square here? Well, and why do we have to move this to 0? Well, to do that, let's go back to section 1.8 when we study about linear transformation. In particular, page 34. If T is the linear transformation, then it transforms the 0 vector to 0 vector. That's the first point. So we know it will transform this point 0, 0 into 0, 0. So that's why we have to move this back to 0, so it can transform from the unit square, from this 0, 0 to that 0, 0. Because it cannot go from here to here. This point, it has the 0, 0, yeah, but it's not one of the edge, one of the point on the parallelogram. So we have to shape that, so that one point will be at 0, 0. In that case, we can match, then we can map between unit square into that. That's the first part. And then we say, how do we find the matrix? Well, also in chapter 1, but this is in section 3.1.9. Right here. The theorem on page 36. It says that to find the standard matrix for the linear transformation, all we do is just find the transformation of T applied to E1 and E2 and so on, and the E1, E2 is a column vector of the identity matrix. So to recall, first we have the identity matrix. So it's going to be 1, 0, 0, 1. If we're going to write that as a vector, that will be E1 and E2. So E1, E2. Now, the theorem says that the matrix for the transformation will be given as A equal to the transformation of E1 and then the transformation of E2. I will stack that into a matrix. So that's why we need the unit square, because the unit square, what is the coordinate of this point? Zero and 1. And this one is 1 and 0. So essentially this is E1 and this is E2. Right? So that's why we have the unit square here, because that gives us E1, that E2, 1, 0 for E1, 0, 1, E2, conveniently. Now we just map, right, to find the transform from here to here. Just map that in the clockwise orientation. So if we map 0 to 0, which is good, so it will map this point. We map this point into this point. And then was that point into that, and this point map into this. So in that case, what is A? From E1, from E1, it mapped to the point 6 and 1, so the matrix is 6 and 1. And then from 0, 1, which is E2, it mapped to 2 and 5. So yes, so that is the matrix for the transformation. Or if we want to write down the actual transformation, we can say it will transform upon xy, so that the first coordinate, we just multiply this by xy, so 6, 2, 1, 5 multiplied by xy, so we have 6x. I'll just write that in the matrix form, it's easier to see. Multiply, that will be 6x plus 2y and x plus 5y. So this is the transformation. We go from xy to 6x plus 2y and x plus 5y. As you see, if we put 0 and 1 here, we have 2 and 5, and so we have the parallelogram. So once again, we have to move the parallelogram so that we have 0, 0, so we can map with the unit square. The reason we use the unit square is because from the unit square we have E1 and E2. That's always there. So we can find the transformation, the matrix for the transformation by transform those E1 and E2. So that's what we have here. And finally, we just use this theorem. So let's call this is the area of S. Of T of S. And this is S, the unit square. So we transform a unit square S into T of S. So we say area of TS is equal to the determinant of the matrix of course, we can use those simple 2 bars for determinant. That times the area of S. So determinant of A will be 6215. The area of S, the unit square, that's convenient, it's just 1, right? So it's going to be 30 minus 2. So that's going to be 30 minus 2, just 28. So the area of the parallelogram is 28. Right. So it's nice enough, right? So what we did, once again, what we did was just write the matrix so that write the parallelogram so that move it so that one vertex is at 0. The next vertex will be mapped to E1 and E2. We're just going to draw it so it has the orientation correctly. And finally, we just find the area using this formula. The area of the transform image is equal to the determinant of the matrix of the transformation times the area of the pre-image. Right. The little note here we write is that remember, if here we have the determinant is not enough, make sure that when we write like this, make sure it is not just the determinant, it has to be positive. So that's why write like this might be a problem later, because the absolute value, the 2 bars is for determinant, not for absolute values. So potentially determinant could be negative. So make sure that in the formula it actually is absolute values of determinant of A. It would be confusing if we write A like that. That of course could mean something else later, but we have to have determinant of A, and that's what I want to write in the note here. Note, remember the area has to be positive, so in the formula should be absolute values of determinant. Area is greater than or equal to 0. So we have to have there is absolute values in the formula, so make sure that it's going to be positive. So there's the absolute values. So that's the little note. Right, here. Now let's consider another example. Now this is completely different things. What we have in calculus 1 is just substitution rule. Right, very simple integration. I'm not going to focus on the result here. Right, so now just look at this substitution. We go from integral in terms of x, term the integral in terms of u, and this is the transformation. The substitution. when we do that, let u equal to x plus 1, we have dx equal to du over 2. And when we do use the substitution, when x equal to 2, u equal to 5, and when x equal to 0, u equal to 1. And then dx is equal to du over 2, which is, and that we write this, and that's what we have. Now notice that original integral, we go x from 0 to 2, and then from u we go from 1 to 5. And then we have to have 1/2 to cut this back in half. Right, so when, of course, things will get a lot more interesting when we have something that is not a constant here, because this potentially, if this is x squared, then we have the x in here. But of course that will have something else. But the idea about what we learned here, the determinant and the linear transformation, somehow is related to this. This of course is the bigger picture than what we have earlier. But the idea here, of course, we have twice the length, so we cut that in half. There's some reason to that. All right, now after all of the thing we did on the last problem, it says that the theorem, if we just want to find the area of the parallelogram determined by the column, and then we just say the area of the parallelogram determined by the column of A is the determinant of A. Remember, if we just always have the area of S, that is the units where the area, of course, is 1. So in that case, we don't even need the area of S. We just have determinant of A. Right. So once again, if A is a 2 by 2 matrix, the area of the parallelogram is determined by the columns of A is determinant of A. Right. Now, another example. Find the area formed by following points A1, 5, B is 3 and negative 2, and C is negative 2 and 1. So of course we just plot those points 1 and 5, 3 and negative 2, 1 and 5, 3 and negative 2, and negative 2 and 1. Alright, so we have kind of that triangle. Right. Now we have to move it so that we have one of the vertex at the origin. So we do that as a, of course we can move the whole triangle here or here, it doesn't matter. I'm just going to move that, going to be into here. Yeah. So that point move here. So everything will shift 2 units to the right and 1 unit down. So 2 units to the right plus 2 and going down minus 1. So we're going to do that to all the corner. So that point goes here, that point goes here, and that point goes there. So this is the triangle that we have. Right, the coordinates. Of course, 0, 0, that easy. What is the coordinate here? So plus 2 and minus 1. This is A, plus 2 minus 1. So that will be 3 and 4. 3 and 4. And this is going to be this point plus 2 and minus 1, so it's going to be 5 and negative 3. Right. So now we just match. What we match, of course, this time is not matching with the unit square what we match is with this triangle. Because here is still 1, 0, and 0 and 1. Right. So let's map 0 to 0. That's naturally. And then the next one, so we match so that it will be the same orientation. So in that case, the transformation is going to be what? Right, transform of E1, which is this point, is 5 and negative 3. And the we have to write as a column too. And transform of 0 and 1 is going to be 2 and 4. Right. And now let's say this is S. And this is T of S. So we say area of T of S, which is that triangle, equal to the determinant of A. Don't forget, in the absolute values times the area of S. Area of S here is not the unit square, so only half of it. And determinant here, 20 minus 9 minus negative 9, so that's 29. So the area is 29 over 2. The area of the triangle. Right. Now, and then we said, what if we don't have to move the point? Can we just do that without any drawing? Well, of course, certainly we can. Right, so the answer, what we have now, let's say we don't have any drawing at all. We have the point A is 1 and 5, B 3 and negative 2, and C negative 2 and 1. Now in pre-calculus, when we find the vector, let's say the vector that connecting A and B is going to be the point B minus point A, and same thing AC is going to be point C minus point A. Final minus initial, that's how to find the vector. Right. B minus 8, B minus A, 3 minus 1 is 2, negative 2 minus 5 is negative 7. Of course, if we write that as the vector in pre-calc, let's try using the triangular bracket notation. Or if we write a vector, well, column vector. So in the next section, in the next chapter, we'll see that vector is just something that has more than one component. It doesn't really how we write it. We could write as a point, could write like that, or could write as a column vector. Now AC, C minus A, so negative 2 minus 1 is negative 3. 1 minus 5 is negative 4. Right? Or negative 3 and negative 4. Right, so this is a triangle formed by those two vectors. If it is the parallelogram, we need 4 points, so in this case, but the area of the triangle is of course half of that, so area now of a triangle, I just draw I draw a triangle really, it's going to be 1/2 determinant of A, where A formed by these columns. So we have 1/2 determinant of the matrix 2, negative 7, -3 and -4. Right, so that gives us 1/2. 2 times -4, that is -8. Minus -21. Remember, that's why we need the absolute value, because determinant in this case negative. So we have 1/2, and that is 29, and that's 29/2. Right. So there are a lot of things that we can get from this example. First of all, if we want to find the area of the triangle formed by the two vectors, perfectly fine. Just find the two vectors stacked in columns. Determinant of that, don't forget the 1/2, because the area of the triangle is half of the area of parallelogram. So that's the first thing, right? Right. Now the advantage of the triangle is that we don't have to worry about the case where we have 4 points in the parallelogram. So what do I mean by that? Let's say I give you 4 points, A, B, C, and D. Of course, when we draw it out, we know that the parallelogram is formed by these two vectors. And not between A, B, and C, D. So we don't know the orientation. In the problem, I give you 4 points A, B, C, D. It could be formed by A, B, and AC. Could be formed by something else. So just like the last example, we have to draw it out. So we know that if we want to form two edges of a parallelogram, we're going to use those 2 points and those 2 points to form an edge. We don't need that point. Right? So, once again, the area of the parallelogram is found by the vectors, two vectors, is equal to determinant of that. Right? So once again, it just shows that we can use those two vectors just like this. But if we move the triangle so that the point here is going to the point here at the origin, and then we have the triangle here, or we move that on that side, so this will be at 0, 0. It doesn't matter. What matters is that when we're trying to find the area of the parallelogram or the area of triangle, in that case we cut in half, we need the two vectors that form the parallelogram. Right, let's just say if A is a 2 by 2 matrix, the area of parallelogram determined by the columns of A, meaning that we need to form the parallelogram. We need to know two vectors on the adjacent sides of the parallelogram, because in this case, if I have AD, that is not the parallelogram we want, that is different parallelogram with AB and AD, right? So bottom line is, when we have 4 points, just draw it and see which one actually will form a parallelogram. When we draw those 4 points, we know we can use this vector and this vector. Now let's go back to actually doing this. Remember, all we need to do is just find the vectors that form the parallelogram, right? So even though all of these are nice and all, but the most direct solution is this. First, we need to find the vector that connect these 2 points, right? Once again, the final minus initial. Let's say if this is the case, final minus initial. So this vector is going to be, let's say the vector v1 is going to be 3 minus minus 2 and 0 minus minus 2. So of course we go 5 units up and 2 units to the right. So that is the vector on the edge of the parallelogram, one of them. Now when we do the drawing, we can see that this is the second one, and that is v2, which is what? Minus 1 minus 2, that's minus negative 2, that's 1, and then 4 minus minus 2, so it's going to be 6 and 1. So 6 units to the right and then 1 unit up. Right? So we can say the parallelogram is formed by those two vectors. And now if we have those two vectors, put in the matrix, take determinant, take absolute values. That's pretty much it, right? So now we have those two vectors. If we just want to find the area of the parallelograms formed by those two vectors, just put in the determinant, right? Five. Oh, we just say in this case, it's not 5 and 2, it's 2 and 5. Sorry. Actually, we can see that those are the vector 2 and 5 and 6 and 1. Yes, those are the vectors. So in this case, the parallelogram formed by these two vectors 2 and 5 and 6 and 1. So once we know the vectors on the edge of the parallelogram, what we need to do is just find the determinant. In this case 2 minus 30, so determinant is negative 28. But remember, the area have to be positive, so we take the absolute values. So from here, area is equal to absolute values of that determinant. So 28, which is exactly what we have here. So don't have to go through all the problem. When we are given the points, at least draw it out so we know which one will form the two edges, the two sides of the parallelogram. One we know the vectors that form the parallelogram, put that in the matrix, find determinant, take absolute values so that we have a positive answer. Simple enough, right? Have the points, put in the parallelogram, see what are the two vectors on the edge. Of course, you can use this vector and this vector as well, as long as two of them on the edge, like this. Of course, that vector is the same. So find two vectors on the edge, and then put in the matrix, find determinant, find absolute values if it's not positive, and that's pretty much it. If we want the area of the triangle, well, cut that in half. But still, we need to know two vectors on the edge of the triangle. We need two sides of a triangle, and then put in the matrix, find determinant, find absolute values. It is a triangle, so cut in halves, right? Now, even more interesting is we have scenarios here. Let A and B be positive number, find the area of the ellipse bounded by that equation. Now, this is the ellipse. If we want to draw a square is between, let's say this is x1, x2. A square is between x1, so we're going to go a unit left and a unit on the right. B square below x2, so b unit up and negative b unit down. So with that, we form an ellipse. Actually, it is, we form a rectangle first. The ellipse though is going to be inside that box. So this is the transformation of something. Right. Now, what we actually transform is transform to something that has the vectors of 0, 1, 1, 0, and that of course is the unit square. So instead of the unit circle, instead of unit square, this time it is the unit circle. So in that case, what we transform, again, we still need the point 0 and 1. So this is actually 1 and 0, or the vector 1 and 0. Here is 0 and 1, or the vector is 0 and 1. Yeah, so we need those 2 points. And let's say we map this point to that, and this point to this, of course 0 to 0, so that's natural, right? So what we map is, what we say is T of E1 and T of E2, that will give us the matrix transformation, right? And that equal to what? E1 1 and 0 map into A, this point is A and 0. E2 is going to map to this point, which is x equal to 0, y equal to b, so 0 and b, so that is the matrix A. And finally we have the formula area of TS, which is the area of the ellipse in this case, equal to absolute values of determinant of A times the area of S. Right, determinant of A, of course that's just AB. And what is the area of S? Area of S here is just the unit circle, pi r square, and the radius is 1, so we just have AB times pi r square, which is 1 square, so this is going to be pi AB, right? So it's turned out to be very nice. So the area of the ellipse is given by pi AB. The area of the ellipse bounded by this equation is given by pi AB. So turned out to be very nice, and we actually use a transformation here. So once again, if there's something different than this, because we use that formula, but quite often we transform that to the unit square, and the area of the unit square is 1, so we really don't need that multiplied with the determinant, absolute values of the determinant. In general, we do need that. In this case, the area of S is not equal to 1, it is pi, so it's different. Right, so once again, there's a lot to cover in this section. First of all, the Cramer's rule is simple enough. And next, we can use the inverse to form the aggregate of A, and then from that we find the inverse. We almost never use it. And now we can use the determinant to find the area of the transform of the image. So in this case, if it is parallelogram, find 2 vectors that form the parallelogram, put it in the matrix, find determinant. Because the area of S in this case is 1, so it's not really important. We just have determinant of A with absolute values. If it is a triangle, cut in half. And if it is some other shape, make sure we know the area of S as well. But with that, we finish section 3.3. As always, thank you for watching, and see you in another video in linear algebra.